¿Cambiaron el reloj?
Sí, creo que sí.
Es distinto.
Está con la hora de ahora.
Sí, me acuerdo que era otro reloj y nunca estaba a la hora. Hola, muchas gracias. Gracias. Entonces, al final, ¿en inglés o en español?
Vaya, varios que no hablan español.
Ok.
Sí.
En inglés entonces. Claro. It's no democracy.
Muy bien. Buenas tardes. Pues qué bueno que hayan venido, a pesar de ser coloquio en el viernes, y a muchos de nosotros incluso a punto de salir de viaje para el Congreso en Cozumel, ¿no? Bueno, es un gusto presentar a los que no conocen al doctor Iván Lacerna. Él estuvo como postdoc acá 2 años en el Instituto, trabajando conmigo y otros colaboradores. Iván terminó su doctorado en la Pontificia Universidad Católica de Chile, trabajando con cuestiones de modelación de evolución de galaxias con métodos seminalíticos. Aquí también estuvo trabajando un poco con eso y con algunos aspectos también de observaciones. Por ejemplo, este trabajo es parte de algunas de las cosas que estuvo haciendo aquí. Actualmente Iván trabaja en la Universidad Católica de Chile y un convenio con el Max Planck Institute en Heidelberg como astrónomo de soporte, ¿no? en la silla. Entonces su experiencia astronómica ha ido creciendo vertiginosamente, teoría, modelación, observaciones ahora, y bueno, se va perfilando como un astrónomo muy completo, como debe de ser, ¿no? Entonces es un gusto tener aquí a Iván, y él nos va a presentar entonces este trabajo sobre las galaxias elípticas aisladas, ¿no? Adelante.
Sí.
Creo que la va a dar en inglés porque, bueno, hay algunos que no hablan español, ¿no?
Yes. Well, hello everyone. It's a really pleasure to be here. As Vladimir told us, I was a postdoc here. This from picture for my 2 years here at UNAM. It was a very nice experience. I met very nice people, very great researchers, very fantastic friends. So it was a very great experience. So I'm very happy to be here again in this auditorium to give this talk. I would like to mention some collaborators, people from UNAM, as Héctor Hernández, Vladimir Ávila, and Juana Bonza. Juana Bonza is a licenciatura student at UNAM, and Asociación del Olmo from Spain. Well, my present is this. I'm a postdoc at the UC Center for Astroengineering in Santiago, Chile. This is the building, which is called Centro Innovación, located at the south of Santiago. The Astroengineering Center is located in the 6th floor in this very nice campus, Campus San Joaquin. You can see the Andes in the background when it's possible to see it, because usually Santiago is have a lot of pollution and clouds, but when the day is good, you can see the Andes itself. And also, I'm a support astronomer at the MPG ISO 2.2 meter telescope located at La Silla Observatory. This telescope this is the telescope. It's operated by the Max Planck Institute of Heidelberg, but it's located in Chile. So in order to have an idea of of the location of these places. Here is Santiago. This is a map of Chile, the central region of Chile. This is Santiago. This is where is located the Astroengineering Center. And here is the La Silla Observatory between Lacerna and Copiapó. In front of La Silla Observatory, 40 kilometers to the north, is located Las Campanas Observatory, where the apogee south instrument will be located, where here the Institute is member of the collaboration of the Sulan 4. Here to the north is Antofagasta. Here in this place is Paranal, where is located the BLT telescopes. And other important part of the observatories in Chile is ALMA, which is located in this part, in the Atacama Desert, very close to the frontier of Argentina and Bolivia. So in this region is part of the Atacama Desert. The La Silla Observatory and Las Campanas are located at the end of the Atacama Desert. Here is Tololo, and Gemini South, and here is Paranal, and here is Alma. Well, about this talk, among the wide diversity of morphological types, elliptical galaxies seems to be those objects that are located in the final stage of transformation and quenching of the star formation activity in the evolution of galaxies. They usually are found in very high density environments like this, a galaxy cluster. They have very few amount of gas to trigger new star formation episodes. They have red color as a consequence of an old stellar population, very high metallicities. So the people usually talk about the elliptical galaxy as red and dead objects. But in this picture, about these galaxies are red and dead, with picture which is clear for galaxies located in a high density environment, it's not clear what is the situation about ellipticals located in an opposite environment, in a low density environment. For example, at a given stellar mass, the colors of the elliptical galaxies in high density environment are the same as ellipticals in low density environment? That answer has not been answered. That question has not been answered before, for several reasons. One of them is generally the people split the galaxies in two morphologies: late type galaxies, early type galaxies. So most of the work understanding the properties of this kind of galaxies is taking samples of early types. The early types include ellipticals and also lenticular galaxies. Lenticular has some properties which are more similar to a spiral. In this work, we just use elliptical galaxies. We are not including lenticulars. Another difference is that people, when try to compare the properties regarding environment, use high density populations, for example, in cluster, and also the field. In our case, we use a very extreme condition isolation, very, very, very extreme. So we can study these properties in more detail. Here is the samples that I will use in this work. Ellipticals located in a very high density environment, which is the Coma supercluster. This is the position of these galaxies. This is the declination and right ascension. The triangles correspond to the members of this supercluster with spectroscopic redshift confirmation. The red triangles correspond to ellipticals in this region. Okay? This supercluster is composed mainly by two massive structures, the Coma cluster and the Leo cluster, and other groups and filaments around these structures. We have a sample of around 100 ellipticals, classical ellipticals, we could say. And we are selecting a sample of ellipticals in an absolute opposite environment using this catalog of isolated galaxies from Hernandez Toledo et al. This catalog is called UNAM-KIAS from the year 2012. It's a sample of 1,500 galaxies. They use the data release 5 of the SLOAN, the original sample was 300,000 galaxies. And from these 300,000, they just select 15 galaxies, 1,500 galaxies, which are very isolated. The selection criteria is as follows. The projected separation of a candidate galaxy has to be 100 times larger than the radius of any neighbor around the candidate, or the radial velocity difference has to be larger than 1,000 kilometers per second. Sometimes there are other conditions. Maybe there are neighbors which are smaller in this 3D criteria between the distance, the projected distance, and also in the radial velocity. But if the neighbor is very faint or very less massive than the candidate galaxy, this candidate galaxy is classified as isolated. This condition of faint is a difference between the candidate and the neighbor galaxy of 2.5 magnitude. This corresponds to a factor of 10 in brightness. So in this case, you are assuming that this faint object is not a relevant perturbator, is not altering the properties of the candidate galaxy. So this galaxy can classify as isolated. This is the distribution in redshift of the isolated galaxies. The open histogram corresponds to late-type galaxies. The red histogram is for early-type galaxies. In this sample, there are 300 early-type galaxies with visual morphological classification supported by statistical analysis, for example, Fourier analysis, position angle, ellipticity. From this sample around 300 early types, there are 90 elliptical galaxies. In this table, you can correlate the morphology with a parameter which is called T. We select galaxies with T equal or lower than -4. Usually the early type galaxies have negative values. Late type galaxies have positive values. We are using just this kind of a galaxy, very early type morphologies. We are not including lenticulars, and also we are not including late types. It's interesting that there are people that are, in the past, in the literature, you can find some studies about isolated elliptical galaxies. But the sample is just a few members, 5 galaxies, 10 galaxies, 20 at most. In our case, we have a sample of 89 isolated elliptical galaxies at redshift lower than 0.8. They are nearby galaxies in the local universe. And we can compare in a statistical analysis for first time with these 100 classical ellipticals located in a massive structure, which is called the Coma supercluster. So in this plot, I show the color as a function of the stellar mass for isolated elliptical galaxies in squares, and also the ellipticals in the Coma supercluster in triangles. These colors, this square with colors correspond as subsamples of isolated ellipticals, and I will refer to these subsamples in a few minutes. The important here is that in this line, the red solid line, you can split the galaxies in terms of color. Above this line are the red galaxies, are the blue galaxies. No, red galaxies, and here are the blue galaxies. Yeah. You can see that most of the ellipticals, regardless of the environment, are red. That is an interesting result. However, there is a larger fraction of isolated ellipticals that are blue toward lower masses. So we found that 20% of the isolated ellipticals have blue colors compared to 8% of the ellipticals in the Coma supercluster. So there is a slight trend that you can find more blue elliptical galaxies, which is not expected by the classical concept or classical picture of elliptical galaxies, in isolated environments. Here, in this histogram, is just the distribution of the stellar mass. The gray solid histogram is the distribution of stellar mass for the isolated galaxies. The red open histogram is for the Coma cluster. And here the distribution in terms of the color. And you can see the colors are more or less the same on average. What you have larger dispersion in the color in the case of the isolated galaxies. There are a few of them, 8%. There, on the right figure, we have the star formation rate normalized by the stellar mass of the galaxy. This is called the specific star formation rate as a function of the stellar mass. Again, this line split the population between star-forming galaxies and passive galaxies in terms of the star formation activity. Again, most of the ellipticals, regardless of the environment, are passive. So the general picture that the elliptical galaxies are red and dead is true. Most of the ellipticals are red and dead in terms of the star formation, regardless of the environment. That is true. But again, there is a small fraction of isolated ellipticals that show star formation activity. In blue colors, I showed those galaxies that at the same time are blue and star forming. In the rest of the talk, we will refer to these galaxies as blue star-forming elliptical galaxies, which are, again, are not common. You expect this in the case of spirals. You don't expect blue and star formation in ellipticals. So it's interesting. It's very small. We have just 4 cases, but it's interesting. In addition, we have another interesting subsample, which is called the recently quenched ellipticals, which are here in this plot are shown in the open magenta squares. This is a color selection criterion developed by McIntosh 2014, et al. 2014, to identify this population. Basically, you have a color. Holden 2012 described more or less this region in the thick black line, where passive galaxies are located. Again, most of the ellipticals are passive. You can see here that the blue star forming outside this region. But they identify a first generation of ellipticals. This first generation means there are ellipticals that acquired this morphology very recently, short time ago. And recently, they have been quenched, which when the star formation activity is disappearing in a galaxy. So in this triangle, they say that you can find this population of recently quenched elliptical galaxies. It's interesting that the 10% of the isolated ellipticals are in this region. And we plot this galaxy in magenta squares. But there are no galaxies in Coma in this region. In this plot, I showed this 10% of the galaxies here. And you can see that more or less they are in a transition region between the blue cloud to the red sequence here. And here, they are very close to this part of the diagram, where you are separating the passive and star-forming galaxies. So it's interesting that in isolation, you can identify these 2 populations that are not found in a usual high-density environment. On one hand, we have these blue star-forming galaxies, and on the other hand, we have these recently quenched elliptical, first generation elliptical galaxies. So that is very, very important because these are unique samples to study the galaxy formation, galaxy transformation, for example. If these galaxies are actually first generation elliptical, you can study galaxy transformation very recently in these objects, and also what are the processes that trigger star formation activity in this kind of morphology. We also study other properties, for example, the effective radius as a function of the stellar mass. In general, if the galaxy is larger, they are more massive. It's a very well known correlation. Here, again, they are the isolated and Coma. We don't find any significant difference in the radius of the galaxies as a function of the environment. Here we have 3 lines that correspond to previous study of this relation for Illy-type galaxy in general. We found that the trends are more or less similar to the literature. But there is an interesting point in the low mass end that some people mentioned that this relation at the high mass end is continuous to the low mass galaxies, But there are people like Mosley that mention that there are a lower limit in the radius of the elliptical galaxies. So here, this part should be flat. And in our case, we found the two classes, galaxies that are an extension of this sequence, other two galaxies that are flat. So maybe here, this part in the relation is not unique. This relation between radius and mass is probably not unique. There is no, on the other hand, here is the light-weighted stellar age as a function of the stellar mass. Here, this property does not show any dependence with the stellar mass. It's just a cloud of points. But again, the interesting point is the interesting result here is that the blue star-forming galaxy, as expected, are the younger galaxies in our study. So a first summary of this result is, regardless of the measurement, most of the ellipticals are redundant. So that sentence is true. However, there are some differences. Among the isolated ellipticals, 20% are blue. In contrast, in the case of the Coma elliptical, this fraction is 8%. 7% are star-forming in isolation, and around 5% are blue and star-forming. In the case of ellipticals, this fraction is lower than 1%, and there are no blue star-forming galaxies. 10% of the isolated ellipticals show evidence of resin quenching, and that is not detected in the case of ellipticals, in ellipticals in the Coma cluster. And also, it's interesting that if you see the blue Coma galaxies here, they are not quenched. But there is an interesting population of blue isolated elliptical that are recently quenched. That could be a hint that the evolution to the rest sequence maybe is faster in isolation compared to a high density environment. So here is a summary. This is a hint that we need to be studying in more detail in the future. It seems that the quenching and reddening is quickly in isolation. For elliptical galaxies. But taking into account that if they are first generation ellipticals, maybe there are some spirals that are evolving more faster. So, but yeah, here is just taking into account the ellipticals. Yeah, in a cosmological context, in this part of the talk, I will present a cosmological context of the isolated elliptical galaxies. Here is a color magnitude diagram, color and magnitude. Here are the bright galaxies, here are the fainter galaxies of these two populations. Again, the square is for isolated ellipticals. The triangles correspond to the ellipticals in the Coma supercluster. Here you can see that they have the same trend. But you can see that the blue star-forming galaxies are different from this general trend. This line corresponds to a result of Niemi et al. 2010 using semi-analytic galaxies. Semi-analytic galaxies correspond to a modeling where you use a skeleton. The skeleton is a dark matter simulation where you evolve dark matter particles and then from redshift, I don't know, high redshift 50 or 100 to redshift 0. Then you identify virialized structures, which are called dark matter halos. The current cosmological paradigm says that the galaxies are formed inside these dark matter halos. And then you identify different outputs in the simulation, for example, redshift 50, 40, 30, 20, 9, 8, 0. And you populate galaxies inside these dark matter halos using analytical recipes. For example, using a Kennycoot-Smith law or other relations that are related with how the galaxy can trigger star formation activity and how the galaxy can grow in stellar mass and evolve the morphology and something like this. And in this case, Niemi et al. Used the Millennium simulation and uses the semantic model of the Lucia et al. 2007, which is a very known semantic model. So they identify elliptical galaxies in this simulation. Elliptical galaxies are here shown in the blue points. The solid, the dashed line corresponds to the relation in this color magnitude diagram for the ellipticals. And also they identify isolated elliptical galaxies in this simulation. The definition of isolation is bit different compared to our definition of isolation. We need I have to say that. But in general, they are isolated galaxies. They are different to these elliptical galaxies. They are shown, these isolated ellipticals in the model are shown here in this yellow diamond. And they found a different relation in the color magnitude diagram, especially that in this part, in the blue faint region of the magnitude diagram, they identify 20%, 25% of the isolated ellipticals should be located in this region. That is the prediction of the semitic model. They, in that moment, in 2010, they identified with an observational sample of isolated galaxies, and that sample was from 2004, from a work by Reda et al., with just 7 isolated galaxies and 7 massive isolated galaxies. You can compare with, in our case, that we have almost 90 isolated elliptical galaxies with different magnitudes and different stellar masses. So here are the same lines of the previous plot. Here the dotted line is for classical ellipticals. Here the solid line is the relation that Niemi et al. Found for the isolated ellipticals and the models, and there is a trend, very similar trend that, okay, most of the ellipticals are located here, but our blue star forming follow this trend predicted by the semitic model. But we find a significant difference in diffraction. They predict that 25% of the isolated ellipticals are blue and faint. In our case, just 3 or 4 cases. Actually, you can see that the fainter isolated galaxies in our case follow the expected trend. So there is a difference in the prediction by the models and observations. Furthermore, we compare the color and the specific star formation rate, but this time as a function of the halo mass, the total mass which is located the galaxy. The total mass is obtained from a catalog of Jan et al. 2007. It's a catalog that tried to identify groups in an observation using the Sloan data. And it's interesting, but they can identify groups with just one single member. It's not magic. They have a interesting criterion, but I will not talk about that in this part. But we can identify the halo mass of this galaxy as a function of the color and a specific star formation rate. Here, the dotted line is the prediction of Niemi et al. 2010 for elliptical galaxies in the semitic model. They say the ellipticals are more or less flat in this relation, but in the case of isolated, we find that to lower halo masses, the isolated galaxies are bluer. This is kind of downsizing in terms that in the cosmological paradigm, the massive structure are formed recently, and the lower massive structure formed long ago. But in observation is different because the galaxies in the more massive structure are red and old, and in our case, in the low mass end, these galaxies are bluer compared to this one. A similar trend is seen for the star formation activity, that in the low mass end, you identify these star-forming galaxies. So a summary of this part: isolated ellipticals do not reside in massive halos. This is an interesting point. Usually the groups and cluster have halo masses above 10 to the 14 solar masses. So here in the case of the isolated ellipticals, they have masses in the region between Milky Way galaxies. Milky Way galaxies have a total mass around 10 to the 12 solar masses, and poor groups, 10 to 13, 10 to 13.5 solar masses. We detect downsizing in mass. If galaxies are located in massive halos, they are old, they are red. The models predict a too high abundance of blue faint or low mass isolated ellipticals with respect to our observational results. That means, independent of the definition isolation, of difference of morphology, how do they define a morphology, an elliptical galaxy, how do we define the morphology of the galaxy in a simulation, which is very, very difficult. We think that the most important reason for this difference is because some physical processes related with the gas in galaxies is not considered in a star formation. Okay. So, for example, it could be very interesting I think it could be very interesting to have to perform this same plot using hydrodynamic simulation, where the dark matter particles are evolved along with baryonic particles. The problem is that in hydrodynamical simulation are very expensive in terms of the computational cost. It takes a long time to run a big simulation like hydrodynamics. There are two new hydrodynamic simulations with a big size in order to study statistics. One of them is the Eagle simulation, the other one is the Lustre simulation. One of the ideas is to study this kind of feature using these two big hydrodynamic simulations in the future. Here in the final part of the talk, we try to understand the properties of some of the isolated elliptical galaxies. Here in this case, we use the VBT diagram, which is a massive diagnostic diagram used massively by the people to identify the source of ionization of the emission lines. We identify 40%, we identify that 40% of the elliptical galaxies have emission lines with a significant, well, more or less significant signal to noise in both isolated and this environment. So we can plot this VBT diagram for these isolated, for the isolated galaxies and for the elliptical galaxies in the Coma supercluster. Here is the region for IGN. So that means that most of the emission lines of the elliptical galaxy is not a stellar component. It's given by this by AGN in terms of the Seyfert or liner. Most of them are liners. But there is a fraction of ellipticals that are located here in this transition region between AGN and star-forming nuclei. There is a slight larger fraction of isolated in this region, 11%, compared to the Coma cluster, which is 8%. Here, the Coma cluster is in red circles. The isolated ellipticals are in squares. One of our blue star-forming galaxies is actually a liner. It's not a very real star-forming galaxy. It's a liner galaxy. Other galaxy here the number is the ID in the UNAM-KIAS catalog. This is the galaxy 613 in the UNAM-KIAS catalog. This galaxy, according to the emission lines, could be a transition galaxy between star-forming and AGN. But if we study in more detail this galaxy, actually this corresponds to a Seyfert. But other two blue star-forming galaxies probably are real star-forming nuclei. This galaxy 613 is very interesting. We did a very detailed analysis of this blue star-forming galaxy. The spectrum is shown in the black solid line. We modeled the spectrum with the emission lines in red lines, with the red lines here. Here is a zoom of the H alpha region, and this H alpha region have a blue component and also a broad red component. This feature is typical of a Seyfert galaxy. So this UNAM-KIAS 613 probably is a Seyfert galaxy. Using the spectrum from the SLOAN, we constructed the star formation history of this galaxy. Here is the loopback time. The dot dash line is the light-weighted stellar population for the blue star-forming galaxy. The solid line corresponds to the mass-weighted stellar population for this blue star-forming galaxy. And we find that around 30 to 60% of the present-day luminosity is due to star formation activity in the last gigayear. But this corresponds just to lower than 5% in terms of the mass. That means that probably this blue star-forming galaxy formed most of the stars very early. Probably this galaxy acquired this morphology, elliptical, very long ago. However, for some reason, in the last gigayear, they have a period of enhanced star formation. What the source of the gas for this star formation? We don't know, because there are no other galaxy around this in order to trigger star formation. Maybe there is some gas supply from the cosmic web. maybe there are some recycling of gas inside this galaxy that is remnant gas that is there, and for some reason is triggered recently in the last gigayear. It's something that we need to study in more detail. But in any case, according to our results and also using photometry, we found this galaxy suffered this rejuvenation. They are old galaxy, the morphology was long ago, but for some reason they have this period of the recent star formation activity, rejuvenation. We did a lot of photometric analysis for the galaxies, and we find that they exhibit blue gradient colors. That means here is the center of the galaxy. We are moving to the outside. Outside, the galaxy is redder than in the center. That also is a hint that the galaxy they have some process of gas accretion, and they are forming galaxy in the center. They are forming stars in the center recently. Also here, we detect the blue gradients. Usually, the elliptical galaxy have the opposite component, the opposite. They have red gradients. The galaxies are red in the center, and they are bluer in the outskirts. Okay, so our photometric and spectroscopic results suggest the rejuvenation scenario for the blue and star-forming galaxies. All this data was obtained. All this result was obtained using the Sloan spectrum, which is just a single optical fiber of 3 arcseconds, which is centered in each galaxy. For this elliptical, this corresponds to the inner 2 kiloparsec of the ellipticals. So imagine the amount of information that you could obtain if you have many fibers across the galaxy. Just to know what a single fiber located in the middle of the galaxy, just many fibers across the complete galaxy. That technique is called integral field spectroscopy. For example, MANGA is an instrument which do this kind of techniques. In general, IFS surveys have allowed the study of cinematic and stellar population properties resolved in space. For example, here is a work by Gomez et al. 2016. So here they have a sample of lenticular galaxy, and you can obtain maps of, for example, H alpha across the galaxy. Not just a single point in the middle. You have the map of the H alpha resolved in space. In the past, there have been some interesting surveys of AVS. For example, Sauron, in the beginning of this millennium, with a sample of just 70 Illy-type galaxies. Atlas 3D, in the beginning of this decade, with around 300 Illy-type galaxies. Khalifa, where Sebastián Sánchez SPI, the project, where the idea is to sample around 600 galaxies in the local universe with this technique. The current data release with the data cube have information for 200 galaxies. I think that it will be a new data release very soon. Monday. On Monday, yeah. How many galaxies? The complete data release? Okay, yeah, interesting. Yeah, okay, we will. Okay, if I give this talk on Monday, I will have to change the. Okay, yeah, there's. The conference just to announce the data release. Well. Okay, 600. Another interesting project is performed in Australia, which is called SAMI, with a factor of 6 compared to the Khalifa, with 3,500 galaxies. The early data release have only 100 galaxies. A new revolution is expected in IFS with MANGA, because they will sample 10,000 galaxies, expected by 2020. The selection is given by stellar mass, with a lower limit of 10 to the 9 solar masses, given that you need to cover the AFS for the galaxy. This galaxy has to be nearby, so the redshift samples have a upper limit of 0.15. The spectral range is cover the optical part of the near infrared. 2,000 galaxies have been observed so far, and the first data release is expected by July of this year. along with the data release 13 of the SLOAN. This is an example of the IFUs. These IFU are integral field unit, which is a bundle with many fibers. They have 7 different configurations of fiber. For example, this is the larger configuration with 127 fibers, 91 and so on, and with this small configuration of 7 fiber for flux calibration. This is the kind of science that you can do with AFS, and this is a special case for manga. You have this galaxy, and you have many properties resolved in space. For example, the dispersion in velocity, sulfur lines, reddening. You can do the BBT diagram in order to identify the source of ionization, but not just with a single point. Here the black diamond is with the SLOAN example, with a single point. No, you have now many points given by the whole information of the galaxy. So in this case, for this galaxy, all this part, the center part of the galaxy is like a GN, but the outskirt of the galaxy is a star formation nuclei or transition object. You can do this kind of information, which is very, very relevant. This is another example. There is a galaxy A, which is star forming. There is a galaxy B, which is quenched. You can resolve a map of H alpha, which is a proxy of the specific star formation rate, or map of the Balmer break of 4,000 Armstrong, which is a proxy of the age. So here you have a specific star formation rate as a function of the age. Here you have the young population. Here you have old population. And of course, the galaxy A is younger than the galaxy B. But with the information of manga or this kind of technique, AFS, you can identify how are these stellar population across the galaxy. So in this case, you can see that the inner part of the galaxy is younger than the outer part. But in the case of the galaxy B, the inner part is older than the outer part. And also, the star formation history in the case of the galaxy B was more extended than in the case of the galaxy A. So you can study in more detail the assembly history of galaxies using AFS. So one interesting idea is to study this kind of especially elliptical galaxy with AFS in order to understand in more detail the galaxy formation. So the final conclusions of this talk, the process of morphological transformation and quenching seem to be, in general, for elliptical galaxies independent of the environment. So we can say they are red and dead. However, we identify 2 interesting populations in isolated environment that are not observed in high-density environment. One of them are the blue star-forming ellipticals that probably we have the rejuvenation scenario for them, and the other population which are called the recently quenched ellipticals with recent morphological transformation. So we have some questions which are very interesting to answer. What is the source of gas supply for the rejuvenation scenario? For example, gas cooling from the cosmic web. So here we are saying that maybe the large scale structure where the galaxies are located are important for the galaxy, for the star formation activity in galaxies. Or maybe just an internal process, recycling of remnant gas. What is the main physical mechanism of quenching for the recently quenched ellipticals? You can, with techniques like AFS, you could answer this question. We identify this hint, but we need to study in more detail this point. Is the transition to the rich sequence faster for isolated ellipticals than ellipticals in dense environments? So, as said before, answering this question, we will shed light on the formation and growth of nearby galaxies. They are unique samples in order to understand galaxy formation and galaxy evolution. So, well, thank you very much. Thank you for your attention.
Do we have questions?
Octavia.
Only one. I have 2 questions. I probably missed something during your talk, but I wonder if you could speak more about how how did you derive the star formation for your galaxies? Or in other words, how can you assure that the star-forming galaxies that you claim are star-forming are indeed star-forming dominated galaxies? Another, I do not understand, how do you know that the recently quenched galaxies are actually recently quenched and not much in the past?
Okay. Well, the star formation is derived using the spectrum, the solar spectrum for this galaxy. Using this spectrophotometric modeling, fitting model given by the MPA for the Sloan survey. We use that data. But also we do our own analysis using the starlight code for the spectrum of this galaxy, so we can identify the star formation rate. We have the star formation rate for this galaxy. But it's using a fitting model, using synthesis population distribution, given by this Sloan spectrum, which is not a high resolution spectrum.
But I still don't get how did you derive the star formation, because starlight just gives you the stellar population, but how did you derive the star formation rate?
Well, you using, for example, H alpha lines.
H alpha, okay.
Or D 4000.
Okay.
For the case of elliptical, they have a more conservative estimation. They have a special conservative estimation in those cases. But it's treated in the case of the MPA catalog that we use. And also, your other question is if we can to be sure about the star formation nature of this. Yeah, that's the idea of the BBT diagram. The answer is, okay, most of them are liners, are not real star-forming galaxies. But in the case of the blue star-forming galaxies, okay, two are AGN, one is Cipher, another liner, but these other two probably are star-forming. And also taking into account that we are using just the central fiber of the galaxy. So that's my point about AFS, because maybe with AFS, we are just sampling this part, but what happened here? That is interesting. I think there is a final.
A comment, the MPA takes into account all the photometry to infer spectroscopic positron population, the star formation, not only the center. In the case of the MPA star formation rates, it's taking into account all the galaxies.
Okay, in the case of the starlight, we are using the center. See, we're using the starlight. Yes, the central part.
Well, I just had a comment about the star formation rate as well, because if you cannot use the H alpha line if it's not a star-forming galaxy, because the ionization comes not just from the stars, but also from a possible AGN. So that line is contaminated. The D4000 and other leaks index are safer, but then you don't have the current star formation rate as H alpha. So it's another stage in the star formation rate.
Yeah, that's true. But in general, those galaxies, independent of this source of error, are located in this part. Are passive. So in case you have this galaxy, because your signal is pretty good. For this galaxy, the signal is pretty good. You are confident that most of, given by this T4000, the signal should be very good. And also here is a lower limit. Maybe we cannot estimate what is the we cannot estimate with accuracy how low is the specific star formation rate for this galaxy. That is true.
Yeah.
But so I would say this is an upper limit.
Okay.
Lower limit. It's a lower limit. But in any case, they are not here.
Yeah, but
the
the star
contamination
formation rate for all those galaxies is estimated exactly in the same way, or for some of them you use H alpha, and for some others the D4000?
For most of them, is the H alpha is not strong, they use D4000. But also they use this photometric model that Vladimir told us. I think Mariana has a final question. Okay, the resequence. Thank you. Okay, Macintosh in this paper developed the idea of these resequence ellipticals. The stellar age of this galaxy is lower than 3 gigayears. They have other properties which are very different than classical ellipticals. And they say, given this consideration, probably they formed very recently. It's very unlikely they formed long time ago. Yes. Yes. Yeah, that's the idea. With AFS, with star formation history, we could make this study for this galaxy in order to support that information. Or maybe that's incorrect. Yes.
This is a kind of empirical, like the EPT, just color.
To identify.
Okay, when you talk about the environment of these rejuvenated ellipticals, do you talk about the overdensity of neighbors, or do you consider the topology of the environment, whether they're located in a wall, in a filament, in a void? Do you have information about it? Maybe this is correlated with that.
And the next step is using this topological morphology, this topological environment. This is the next step. Now, in this case, it's just a high-density environment because it's a supercluster, and in the other case, there are no neighbors or no big neighbors around a galaxy. Just in that case, the definition environment. But we don't have the information at this moment. We don't have the information about this large-scale structure or topology performance.
Okay, at least from a point of view of simulations, the accretion rates are very different in such different environments. So maybe interesting to check that.
About the CD galaxies in the supercluster, did you take them in your sample?
Yes, yes.
Where are they? In the, okay.
There are I think these two, for some reason, this galaxy, which here is, no, I think there are these two, yes, these two.
Okay.
Which, if I remember very well, I'm not pretty sure, but I think there is this and this galaxy. I need to confirm, but I know that I confirmed the two more massive galaxies in Coma, and I confirmed that they are here in this plot. Well, I confirmed this 1 year ago, so I don't remember very well, but yeah, it's considered the two bigger galaxies in Coma are in this plot.
And then another is just a comment. It would be very useful to construct the second BPT diagram with the sulfur lines, because if you are saying that they are liners, most of them are liners, that's the only way really to be sure that they are not AGN. You need both diagrams. In your slide, where you have the manga results, is the second diagram.
Okay.
I think you should do it, especially for the recently quenched beast.
Yes.
Especially for that beast. It's very nice.
Okay, at the conclusions of the first part, you mentioned that from what you see that field isolated galaxies, elliptical isolated galaxies, they seem to evolve faster than the cluster ones. Do you have any idea about that? This is very interesting, actually.
What do you mean we have any idea?
If you have an idea about why this is happening, I mean physical reasons.
Yes. It's just a hint. Just a hint because there are no recently quenching these blue ellipticals in Coma. Yeah, I don't have at this moment.
Iván, we can speculate that in a group or cluster, you have some environment, some gas probably. So after the morphological transformation, there is some little chance to catch some of the gas probably in the environment. In the case of isolated, forget about that. Isolated is once the galaxy became elliptical, there is no an environment where to probably catch more gas and continue sun star formation.
There might be also
just a speculation.
that the environment slows down the process of star formation. Not quench completely, but the harassment makes the galaxy consume the gas slower, because they spend a lot of time in the Great Valley.
Yeah, maybe. It's interesting the point of Vladimir because when you have a merger, we suppose that the elliptical galaxy formed by mergers, whatever, the gas that is there, if you are not in a massive system, this gas is depleted and it's moving outward. So yeah, probably it's not gas remaining in that part. So the galaxy is very fast. The consumption of the gas is very fast, and there is no remnant gas. Is in some cases, yeah. Well, I would say it's a very good hint. I prefer to be conservative in this affirmation because it's polemic. Is it true? Yeah, it's pretty good.
That believe that actually the interactions in such environments accelerate the evolution, so you expect to be faster.
Yes.
But I don't believe that from what I've seen so far.
Can you comment on the property, your isolated ellipticals, and in the sense of whether their formation histories are kind of like a fossil group scenario, or that the elliptical has been formed very early on in the universe?
Yeah, the fossil groups usually are massive galaxies. Usually they have a stellar mass around 10 to the 11 solar masses. So for example, in the case of the blue star forming, look at the stellar mass are similar to the stellar mass of the Milky Way. It's very unlikely that you have the blue star forming galaxies as fossil groups, just because the mass. Some people using numerical simulation are studying the fossil groups, and usually the halo mass of the galaxy is 10 to the 14 solar masses. And our blue star forming galaxies are 10 to the 12 solar masses, again, like a Milky Way. Okay, we have some massive isolated, but they are more classical. They are not very different. They are red, very passive. So I don't expect this galaxy correspond to fossil groups.
And the ellipticals that might be formed in the very early universe would also be much more massive? Or
Sorry? What do you mean?
Is there, as in, it's not entirely known whether all ellipticals are formed through mergers?
Well,
or like, as in mergers of large mass spiral galaxies.
Yeah.
Rather than
the very massive galaxies probably are formed by merger of very large spiral galaxies. If happened long ago, yeah, you expect the merger was wet. Yeah.
Right, but can you have an elliptical type galaxy form in the early universe and just evolve?
But you mean in the case of the blue star forming ellipticals? No, or in the case of whatever isolated ellipticals?
Yeah, just isolated.
Yeah, probably the formation mechanism for them is very similar to the classical ellipticals. So you have a wet merger of large spiral, you have a massive, relatively massive elliptical galaxy, and that is I would say the picture is general. That is actually our results support that picture. They are red and that. So we believe that the process of formation in the isolated ellipticals is very similar to the ellipticals in clusters. It's very similar. Maybe there are some difference in this kind of objects. Maybe, or the recently quenched. Maybe, but what is
Just a comment on your question, is that if you think that a fossil galaxy is a byproduct of the end evolution of a group,
yeah,
via some accretion process or merger, then you expect that fossil galaxy or candidate have more or less the same isolation criteria that isolated ellipticals. And in that sense, they share something in common. But as you see, masses are completely different.
¿Alguna última pregunta? Ok, muchas gracias.